We're into it. Yeah.
Why is it like a green fleshy thing?
Sunlight low.
C.
We're round of applause for graphics. Thank you. Now, what I want you to imagine is that we've got reactant A reacting with, because it's a reactant B, give us C and D. Now that could be an acid plus a base, gives us salt plus water. It could be an acid plus an alcohol, giving us an ester plus water. Doesn't matter. This is going to apply to every single reaction from now on. And so that's it. Well, reactants A and B forming products C and D. Now the overall equation for that could look like this. So if we're to write a chemical equation, if it's reactant A, we'll put a little a to symbolize the number of moles. If it's reactant B, we'll put little b to symbolize the number of moles. All right. When we've balanced equations, when we've used numbers to balance the equations, in this case here, I'm just putting letters. So it could be any number. It could be any number. It's just another equation. All right? With letters in front of the reactants and products rather than numbers. It's just an equation. All right? So whatever follows next can apply to every single chemical reaction that we do. And we're going to think about the reaction specifically between hydrogen and iodine. And we're going to look at the table on the next page. And so what I want to highlight is that when we get to the equilibrium constant that we're going to get to a little bit later on, it's an experimental constant. It's not something that's just been plucked from the equation. It'll look like it, but it isn't. It's a purely experimental result that we're going to get for this. Now, there's a couple of things that we need to just take care of. In square brackets here, I've got hydrogen in square brackets. It's hydrogen reacting with iodine. And that little square bracket, we're familiar with that, and we'll get a lot more familiar with it when we do acids and bases shortly. That square bracket has got a very definite meaning in chemistry for physical chemists, and it means concentration. So when we've got something in square brackets, it refers to a concentration in moles per litre. And what we're going to do is try and find out, when we measure concentrations of reactants, when we measure concentrations of products, is there some sort of mathematical relationship between these things? And so I'm going to give you results for actual experiments, and then we're going to see if there is any mathematical relationship between them. So here we go. Now, you've got to imagine for the moment that we can take hydrogen, we can take iodine as gases, and we can mix them together. And let's take a number of different reactions. Now, we've taken hydrogen, we've taken iodine, and we've got some hydrogen iodide. And at equilibrium, now just how we manage to do this, and it's quite sophisticated, we take any amount of hydrogen, we take any amount of iodine, and we get some hydrogen iodide. It's all in equilibrium. But once it's all settled down, no matter what the starting conditions are, once it's all settled down, that's what we've got of hydrogen, that's what we've got of iodine, that's what we've got of hydrogen iodide. All right? That's the first experiment that's been carried out. Now you'll need a table like this. So if you scribble furiously while I'm putting something on the board, normally when I'm organised, you'd have the table in front of you, but you don't. So you have to scribble it down, because I'm going to ask you to do some work with these numbers. We've done another experiment where we've taken hydrogen, we've taken iodine, and we've got hydrogen iodide. And we've let it all settle down, and that's what we've got, 0.2 times 10 to the minus 2 moles per litre of hydrogen, 0.2 times 10 to the minus 2 moles per litre of iodine, and there's 2.96 times 10 to the minus 2 moles per litre of hydrogen iodide. We've mixed the reactants up, we've let them reach equilibrium, and then we've done some measurements. And we're going to, as mathematicians, we're not chemists this afternoon, we're mathematicians. And I hope you're better mathematicians than you are chemists, quite frankly. And we're going to... All right. There we go. Now, I hope that's the last one, because you're having to just do an awful lot of scribbling there. If you had half a decent chemistry teacher, you'd have that in front of you, ready to go. Poor lesson preparation is what we've got, and I'll edit that out when I do this too. Oh gosh, right, that'll be the last set of numbers. So we've got 1, 2, 3, we've got 6 sets of numbers. Now, if you're a mathematician, if you were a mathematician and you were looking for a relationship there, what might you, how might you play around with those numbers? We could do an average. What would an average mean in that situation? Remember, we're dealing with reactants and we're dealing with products. We could add them together and divide by. Yeah, there's lots of different. There's lots of. Or take a mean. There's lots of different things you could do. But what I'm going to suggest to you is that we try this. What I'd like you to do is go down that column and work out what the value of the concentration of hydrogen iodide divided by the concentration of hydrogen multiplied by the concentration of iodine. I'd like you to go down that column as a first guess. I'd like you to go down that column here and work out what that ratio is, because effectively on the top line we've got products, on the bottom line we've got reactants, and we've done the dead simple thing. All we've done is put in the concentrations just to see if there's any relationship. Just to see if there's any relationship.